We're going to continue our exploration of proof by induction now, and we're going to look at a divisibility and multiplicity example. Okay, I'm going to look at an example because in the exam you're going to come up with something very, very similar to this. Perhaps it might be words in a slightly different way, and perhaps it might be laid out in a slightly different way. But essentially, you know, if you can follow what I'm doing in this question, then you should be pretty okay in the exam. And if you can understand what I'm doing in this question, you should be okay in the exam. So I'm going to look at question 7 of the June 2010 FP1 Excel paper. So let's just have a quick look at what it says. The first part is just a bit of algebra. So we're given this, the f of n, so the function is given by 2 to the power of n plus 6 to the power of n. Okay, and we're told in part A to show that f of k plus 1 is equal to 6 times f of k minus 4 times 2 to the power of k. Okay, so the first thing that I want to do is I want to come up with an expression of f of k plus 1. F of k plus 1. Okay, and I'm going to come up with that by replacing n by k plus 1. You can see here that f of n's, f of something, is equal to 2 to the power of that something plus 6 to the power of that something. Well, here my something, my n, is k plus 1. So that's going to be given by, my function is going to be given by 2 to the power of k plus 1, just replacing n by k plus 1, plus 6 to the power of k plus 1. Okay? Well, if you look, that doesn't look like what I want it to look like at the moment. Okay, so I'm going to just use a little bit of a trick here. This 2 to the power of k plus 1, well, let's just have a think about this. Let's just think about general indices laws. Let's say we have 3 to the power of 2 times 3 to the power of 4. Well, that is the same as 3 to the power of 2 plus 4. So when we multiply two things together, we add the powers. Well, here we've got the k and the 1 being added together. So therefore I can split it up into two different indices, I suppose, being multiplied together. So this can be 2 to the power of k multiplied by 2 to the power of 1. Okay, because 2 to the power of k times 2 to the power of 1 is 2 to the power of k plus 1, which is what I want here. And it's exactly the same thing going on with this 6. So 6 to the power of k times 6 to the power of 1. Okay, but this still doesn't look like what I've got here. So let's just have a look and see what I'm after. Well, I'm after something which has f of k in. At the moment, I have got an expression for f of k, so it'd be good to kind of have that expression in my mind. So let's write down what f of k is. So again, I'm going to use this top thing here, this f of n, because you see here now that my n is k. Okay, so whenever I see an n with this, I just replace it with k. So it's 2 to the power of k plus 6 to the power of k. Okay, well now let's compare this thing here to what I've got here again. Now look, I've got 2 to the power of k in here, but I haven't got a 6 to the power of k. Whereas in here, this f of k plus 1, I've got a 2 to the power of k, which is good, that's what I've got in here. But I have got a 6 to the power of k, whereas I haven't got a 6 to the power of k in here. So basically, I'm going to use this f of k, which I've just come up with, to basically try and get rid of 6 to the power of k. So I'm going to say that 6 to the power of k, I just want to isolate this on its own, is equal to f of k minus 2 to the power of k. I've just rearranged this thing to get an expression for 6 to the power of k. Now I can replace 6 to the power of k with this. So, in other words, f of k plus 1 is equal to 2 to the power of 2 times 2 to the power of k. I've just rewritten this 2 to the power of k times 2 to the power of 1, because 2 to the power of 1 is just 2. So I've just then swap the order because it looks neater in my mind. Plus, then again, this is 6 times 6k. I've just rearranged, replaced this. But I've just come up with an expression for 6 to the power of k. It's f of k minus 2 to the power of k. So I've just replaced that thing in there is 6 to the power of k. And I've just come up with an expression for that. Now I'm just going to expand this, and hopefully I'm going to get what I'm after. So 2 times 2 to the power of k plus 6 times f of k minus 6 times 2 to the power of k. 6 times 2 to the power of k. Careful, it's not 12 to the power of k. Okay, it's 6 times 2 to the power of k. Right, because the 6 and 2, I can't combine those into the same base. Right. Okay, and I'm just going to rearrange this. I'm just going to simplify this. Sorry, not rearrange, simplify. So I've got 6 times f of k, and then I've got 2 times 2k minus 6 times 2k. So what's 2 minus 6 of something? So 2 of something minus 6 of something, that's going to be minus 4. of something. So I've got 4 times 2 to the power k. And if you look back at the original question, that is exactly what I've got. So now let's move on to part B. And it says, hence or otherwise. So in other words, the hence bit means that we're going to use what we've just done to answer this next question, which is prove by induction that for all n, which is a member of the positive integers, f of n, this thing is divisible by 8. Okay, so basically we're going to try and use what we've just shown, that f of k plus 1 is equal to this thing in our induction at some stage. It will come clear when we use it. Okay, so let's just remind ourselves of the basic steps of proof by induction. It's 4 steps, the recipe if you like. First of all, we prove the base case. We prove it for an actual number. We stick a number in and see if it actually works. If it does work, we've shown it does work for the base case. We then go on and we assume that a general case is true. So we test an n equals k. Our general case is represented by k, so we put n equals k in. We replace n by k. And we come up with an expression for that, and we assume that it is true. We assume that that is divisible by 8. Okay, we don't know that, but we just assume that it is. We then go on and then we show the next general case is true if the case before is true. So therefore we try and link the k plus 1th case back to the kth case. And then we try and manipulate it and show that the k plus 1th case is divisible by 8 if the previous case is divisible by 8 as well. Divisible by 8 as well. So we kind of use the fact that the previous case is divisible by 8 in our next answer. That will become clear. And the conclusion is just kind of saying the right things in the right order. So let's write our steps down. It shows a good logical thinking to the examiner. So first of all, first step is our base case. So we test our n equals 1th case. So remember, we have f of n equals 2 to the power of n plus 6 to the power of n. That's what we've been given. We need to prove that's divisible by 8. So our base case is when the when n equals 1. So f of 1 is equal to 2 to the power of 1 plus 6 to the power of 1. So I've just replaced n by 1. Okay, and that is equal to 2 plus 6, which is 8. Okay, and clearly that is divisible by 8 because that number there is 8, so therefore we can divide that by 8. It's going to go in there once. So therefore, base case is true. It is divisible by 8. Right? We then go on and we make our assumption step. And our assumption is we assume that n equals k, so we're testing n equals k, is divisible by 8. More specifically, what is n equals k? It's going to be f of k is equal to 2 to the power of k plus 6 to the power of k. We assume that that is divisible by 8. Divisible by 8. Okay? And what I'm actually going to do at this step is just to kind of make this extra specially clear. I'm going to say, well, okay, f of k is going to be equal to some number, x, multiplied by 8. Okay? Why? Well, that is the same as saying that f of k is divisible by 8. Because if it's divisible by 8, then 8 is going to be 8 multiplied by something. It's going to be 8 multiplied by something. F of k is going to be 8 multiplied by something, by some number. I should say where x is a member of the integers. Okay, you don't have to say that, but this is just kind of saying that 8 multiplied by some number is equal to f of k. That's another way of saying that f of k is divisible by 8. Okay? So if x was 2, say it would be 16, which is clearly divisible by 8. If x was 3, it would be 24. 8 times 3 is 24, so that's divisible by 8. Okay, basically it's going to be 8 multiplied by some number, so therefore that's another way of showing it. That's just kind of, the reason why I do that will become clear in the next step, which is the inductive step. And that is when we test n equals k plus 1. Now what is n equals k plus 1 equal to? Well, f of k plus 1, just replace n by k plus 1, is equal to 2 to the power of k plus 1 plus 6 to the power of k plus 1. Okay, but we also know, we've shown in part A, that f of k plus 1, okay, this is where it becomes useful using part A, is equal to 6 times f of k minus 4 times 2 to the power of k. That's what we've shown in the first part of the question. So what we've basically done is we've come up with an expression. We use this. This is literally an expression for linking back f of k plus 1 and f of k. So f of k plus 1 uses f of k in that expression. Okay? Right. And then we basically just go on and fiddle this. And what we basically want to do is have what we're after is that f of k plus 1 is equal to 8 multiplied by something. Okay, as long as this number is 8 multiplied by something here, then we've shown that it's divisible by 8. So that's what we're after. We're after turning this thing here into this thing here. That's what we want to do. Okay. So, how are we going to do that? Well, we've said above that f of k is equal to 8 times some number, 8 times x. So I could immediately just make a substitution for f of k, 8 times x. It's something that I've made up, but basically that's another way of saying that f of k is divisible by 8. Okay, that will help us. So it's 6 times 8x. Okay, and then I've still got this minus 4 times 2 to the power of k. Now remember what I was after? I was after 8 being written out the front here. So I can factor an 8 out of this thing. Okay, and I'll just be left with 6x here. So I factor an 8 out of here. And then I want to factor an 8 out of this thing. Can I factor an 8 out of this thing? Well, look, we're tantalisingly close. If you look at this 4 and this 2, 4 times 2 is 8. So we're really, really close to having an 8 there. But unfortunately, this isn't just 2. It's 2 times 2k. Well, that's okay. We can convert this 2k into 2 times something. Can't we? Because 2 times something, what is that something? It's going to be 2 to the power of, well, this is 2 to the power of 1. This is going to be 2 to the power of k minus 1. Because look, when we simplify this all together, we're going to be left with 2 to the power of, we can combine these two things together, it's going to be k minus 1 plus 1. That's going to be equal to 2 to the power of k, isn't it? So what I've effectively done, it perhaps is a little bit, I don't know, it's a bit superfluous, you might say. But actually, minus 1, and then we add 1 immediately. So that's going to be equal to 0, but actually by just saying that, we can separate it up into 2 multiplied by something, which is exactly what we want, because we want here, we want this thing now. I'll stick in an extra line. This thing is 8, so this is before the factorisation. This is 8 times 6x. Minus this thing now I can write as 4 times this. 2 times 2 to the power of k minus 1. Well, this thing here is equal to 8, which is exactly what I want because I want to factor out an 8. Okay, so I'll just be left with 2 to the power of k minus 1 inside the brackets here. So therefore I've shown now that 4 of k, f of k plus 1 is equal to 8 times something. So it is divisible by 8. Hopefully that makes sense. Okay, I've just manipulated it so that I can have an 8 multiplied by something, because then I know that is divisible by 8. So that's really what you're after with these types of questions. You're after 8 multiplied by something, or whatever number you're dividing by. You're after an 8 out the front multiplied by something. Then you've shown it is definitely divisible by 8. Okay, and then our final step is just our conclusion. And that is just simple as saying f of k plus 1 is true, or is divisible by 8, if f of k is true. Because we've basically assumed, we've used the fact that f of k is divisible by 8 to show that f of k plus 1 is divisible by 8. Okay, so we've assumed the fact that f of k is divisible by 8. Okay, so f of k plus 1 is true if f of k plus 1 is true if f of k is true. Since we've shown that n equals 1 is true, is divisible by 8, then we have shown it's true. We've shown our first domino is true, and we've shown the next dominoes depend on that first domino being true. So therefore we've shown by induction, don't have to say by induction because the question says prove it by induction, that it is true that f of n is true for all n which is a member of the positive integers. Okay, there we are. That's all we have to say by induction. So basically, the thing which you have to watch, the algebra is the most difficult thing there in the inductive step. We have to basically get it to a point where we have our number multiplied by something. It's obvious that then that is divisible by the number which we want, because we've got 8 multiplied by it, so therefore it must be divisible by 8 since we're multiplying by 8.